Welcome, dear traveler of the stars, to a journey unlike any other. Tonight, we drift beyond the veil of ordinary thought, into the depths of space and time, where gravity folds reality and light itself is held captive. As you settle in, let your breath slow, your thoughts soften, and your imagination open wide. This is a voyage into the mystery of black holes, everything we know, and everything we still wonder. If you find peace in the cosmos, consider subscribing, so we may continue this gentle exploration together. Now, let us begin. Long before telescopes pierced the night sky, before equations etched the fabric of space-time, the idea of a black hole was born not from observation, but from thought. In the year 1783, a quiet English clergyman and natural philosopher named John Mitchell pondered the nature of gravity. He imagined a star so massive, so dense, that its gravitational pull would be strong enough to prevent even light from escaping. He called it a dark star, a body invisible to the eye, detectable only by its influence on nearby objects. Though his idea was centuries ahead of its time, it laid the foundation for what we now call a black hole. Mitchell's vision was largely forgotten, until the 20th century brought a revolution in physics. In 1915, Albert Einstein unveiled his theory of general relativity, a new way of understanding gravity, not as a force, but as the curvature of space-time itself. Massive objects bend the fabric of reality, and the more massive the object, the deeper the well it creates. Just a year later, Karl Schwarzschild, a German physicist serving on the front lines of World War I, found a solution to Einstein's equations that described a point of infinite density, a singularity, surrounded by a boundary beyond which nothing could escape. This boundary would later be called the event horizon. At first, this solution was seen as a mathematical curiosity, not a physical reality. The idea of a singularity, where the laws of physics break down, was unsettling. But as the decades passed, evidence began to mount. In the 1930s, Subramanian Chandrasekhar showed that stars above a certain mass could not support themselves against gravitational collapse. They would implode, forming either neutron stars or something even more extreme. Robert Oppenheimer, known for his role in the Manhattan Project, explored this collapse further, suggesting that such stars could form what we now recognize as black holes. Still, the term black hole had not yet entered the lexicon. That moment came in 1967, when physicist John Archibald Wheeler coined the phrase during a lecture. It captured the essence of these objects, regions of space so dark, so mysterious, that they seemed to swallow everything, even light. The name stuck, and with it came a surge of interest and discovery. As our instruments grew more powerful, we began to detect the fingerprints of black holes across the cosmos. X-ray emissions from binary star systems hinted at invisible companions devouring matter. The centers of galaxies revealed supermassive black holes, millions to billions of times the mass of our Sun, shaping the evolution of entire star systems. These were not just theoretical constructs, they were real, and they were everywhere. But what exactly is a black hole? At its core lies the singularity, a point where density becomes infinite and our understanding of physics falters. Surrounding it is the event horizon, the boundary beyond which no information can escape. To an outside observer, time appears to freeze at this edge, as light is stretched and redshifted into oblivion. Inside, the laws of nature twist into forms we cannot yet comprehend. There are different kinds of black holes, each born from different cosmic events. Stellar black holes form when massive stars exhaust their fuel and collapse under their own gravity. Intermediate black holes, though harder to detect, may arise from the merging of smaller ones. And at the heart of galaxies lie supermassive black holes, whose origins remain one of astronomy's great mysteries. How did they grow so large, so quickly, in the early universe? We do not yet know. The study of black holes is not just about distant stars, it touches the very nature of reality. They challenge our understanding of space, time, and information. They raise questions about the fate of matter, the limits of knowledge, and the possibility of other dimensions. They are cosmic paradoxes, both destroyers and creators, erasing the past while shaping the future. As we continue our journey, we begin to see that black holes are not just endpoints, they are engines of transformation. They warp space and time, influence the birth of stars, and may even hold the key to understanding the fundamental nature of reality. In the next segment, we will explore how black holes form, how they grow, and how they interact with the universe around them, from the quiet pull of gravity to the violent dance of cosmic collisions. Let us drift onward, deeper into the mystery. To understand the true nature of black holes, we must first understand the fabric they inhabit. Space and time, once thought to be separate and absolute, are now known to be interwoven into a single continuum, space-time. According to Einstein's general theory of relativity, mass and energy warp this fabric, creating the force we perceive as gravity. The more massive an object, the deeper the well it carves into space-time. A black hole is the ultimate expression of this curvature, a place where the well becomes infinitely deep, and the rules of physics as we know them begin to unravel. At the center of every black hole lies the singularity, a point of infinite density where matter is crushed to an unimaginable degree. Here, the known laws of physics cease to function. Time and space lose their meaning. Around this singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. To an outside observer, anything crossing this threshold appears to freeze in time, its light stretched and reddened until it fades from view. But from the perspective of the falling object, the journey continues inward, inevitably drawn toward the singularity. Black holes are defined by just a few key properties: mass, spin, and electric charge. This simplicity is captured in the phrase "black holes have no hair," meaning they lack distinguishing features beyond these basic traits. Most astrophysical black holes are thought to be electrically neutral, so their defining characteristics are primarily mass and spin. The spin, or angular momentum, of a black hole can twist space-time itself, dragging it around in a phenomenon known as frame dragging. This effect becomes especially pronounced near rapidly rotating black holes, where it can create a region called the ergosphere, just outside the event horizon, where nothing can remain at rest. There are several types of black holes, each formed through different cosmic processes. The most common are stellar mass black holes, which form when massive stars, typically more than 20 times the mass of our Sun, exhaust their nuclear fuel and collapse under their own gravity. The outer layers explode in a supernova, while the core implodes into a black hole. These stellar remnants typically range from a few to several tens of solar masses. Then there are intermediate mass black holes, a class that has long eluded definitive detection. These black holes, with masses between 100 and 100,000 times that of the Sun, may form through the merger of smaller black holes or the collapse of massive star clusters. Though evidence for them is growing, they remain one of the more mysterious categories, bridging the gap between stellar and supermassive black holes. Supermassive black holes, by contrast, reside at the centers of galaxies and can weigh millions to billions of times the mass of the Sun. The one at the heart of our own Milky Way, known as Sagittarius A, has a mass of about 4 million solar masses. How these giants formed so early in the universe's history remains an open question. Some theories suggest they grew from the collapse of massive gas clouds in the early universe, while others propose they formed from the merger of many smaller black holes over time. There is also a hypothetical class known as primordial black holes, which may have formed in the high-density conditions of the early universe, shortly after the Big Bang. These black holes could range in size from microscopic to thousands of solar masses. If they exist, they might account for some portion of the mysterious dark matter that permeates the cosmos. Though no direct evidence has yet been found, black holes are not entirely black. In the 1970s, physicist Stephen Hawking proposed that black holes can emit radiation due to quantum effects near the event horizon. This phenomenon, now known as Hawking radiation, suggests that black holes can slowly lose mass and eventually evaporate over incredibly long timescales. Though this radiation has never been observed directly, it remains one of the most profound insights into the intersection of quantum mechanics and gravity. The boundary of a black hole, the event horizon, is not a physical surface, but a point of no return. Once crossed, all paths led inward. But just outside this boundary, matter can still orbit, forming what is known as the accretion disk. This swirling disk of gas and dust heats up as it spirals inward, emitting intense radiation, particularly in the X-ray spectrum. These emissions are often the first clues astronomers use to detect the presence of a black hole. In some cases, black holes can also produce powerful jets of particles that shoot out from their poles at nearly the speed of light. These jets are thought to be powered by the twisting magnetic fields in the accretion disk and the rotational energy of the black hole itself. Though the black hole swallows most of the matter that comes near, some of it is redirected and flung outward in these spectacular displays, visible across vast cosmic distances despite their fearsome reputation. Black holes are not cosmic vacuum cleaners. An object must come very close, within a few Schwarzschild radii, to be captured. If our Sun were replaced by a black hole of the same mass, Earth's orbit would remain unchanged. We would continue to circle the invisible mass, though the sky would be darker, and life as we know it would not survive the loss of sunlight. Black holes also play a crucial role in the evolution of galaxies. The mass of a galaxy's central black hole is closely correlated with the mass of its bulge, suggesting a deep connection between the growth of galaxies and their central black holes. Some theories propose that feedback from black hole jets regulates star formation, shaping the structure and fate of galaxies over billions of years. Black holes begin their lives in the hearts of stars. When a massive star reaches the end of its life, it can no longer sustain the nuclear fusion that balances its gravity. The core collapses, and if the remaining mass is above a certain threshold, typically around 3 solar masses, it compresses into a singularity, forming a stellar mass black hole. The outer layers of the star may explode outward in a supernova, a brilliant burst of light that briefly outshines entire galaxies. What remains is a gravitational ghost, invisible yet powerful, silently shaping the space around it. But black holes do not remain static. They grow, they feed, and they evolve. One of the primary ways a black hole gains mass is through accretion, the gradual pulling in of gas, dust, and even stars from its surroundings. As matter spirals inward, it forms an accretion disk, a glowing ring of superheated particles that emits intense radiation. This disk can shine brightly in X-rays and other wavelengths, revealing the presence of the otherwise invisible black hole. The process is violent and chaotic, yet governed by the elegant laws of physics in binary systems. Where a black hole orbits a companion star, the gravitational pull can strip material from the star, feeding the black hole and creating a luminous accretion disk. These systems are among the most studied, as they offer a window into the feeding habits and growth of black holes. Over time, the black hole may consume its companion entirely, leaving behind only its gravitational influence and the remnants of its feast. Black holes can also grow through mergers. When two black holes spiral toward each other, drawn together by their mutual gravity, they emit gravitational waves, ripples in space-time that travel across the universe. These waves were first detected in 2015 by the LIGO Observatory, confirming a prediction made by Einstein a century earlier. The collision of two black holes releases an enormous amount of energy, briefly outshining all the stars in the observable universe in gravitational waves. The resulting black hole is more massive, more powerful, and continues its journey through the cosmos. Supermassive black holes, found at the centers of galaxies, grow through similar processes but on a much grander scale. They consume vast amounts of matter, merge with other black holes, and interact with their host galaxies in complex ways. Some theories suggest that these giants began as smaller black holes in the early universe, growing rapidly through accretion and mergers. Others propose that they formed directly from the collapse of massive gas clouds, bypassing the stellar phase entirely. The exact mechanism remains one of the great mysteries of astrophysics. The environment around a black hole is shaped by its immense gravity. Stars can be torn apart if they venture too close, a process known as tidal disruption. The star is stretched and compressed, forming a stream of gas that spirals into the black hole, lighting up the sky in a flare of radiation. These events are rare but spectacular, offering a glimpse into the destructive power of black holes. Some black holes are surrounded by powerful magnetic fields, which can channel particles into jets that shoot out from the poles at nearly the speed of light. These jets can extend for thousands of light years, influencing star formation and the structure of galaxies. The exact mechanism behind jet formation is still being studied, but it likely involves the twisting of magnetic fields in the accretion disk and the rotational energy of the black hole itself. Despite their reputation, black holes are not cosmic vacuum cleaners. Their gravitational pull is strong, but only within a limited range. Objects must come very close, within a few Schwarzschild radii, to be captured. Outside this zone, their influence is similar to any other object of the same mass. This means that black holes can coexist peacefully with stars, planets, and other celestial bodies, unless those bodies stray too close. The growth of black holes is not unlimited. Feedback mechanisms, such as radiation pressure and jet activity, can regulate the inflow of matter. In some cases, the energy released by accretion can push away surrounding gas, halting further growth. This balance between feeding and feedback plays a crucial role in the evolution of galaxies, influencing star formation and the distribution of matter. Black holes also interact with dark matter, the invisible substance that makes up most of the universe's mass. Though dark matter does not emit light or interact with normal matter in the usual ways, it is affected by gravity. Black holes may serve as anchors for dark matter halos, shaping the structure of galaxies and influencing cosmic evolution. Some theories even suggest that primordial black holes could account for a portion of dark matter, though this remains speculative. Black holes, by their very nature, cannot be seen directly. They emit no light, no radiation, no signal that travels freely through space. Yet their presence is unmistakable, revealed through the effects they have on their surroundings. One of the earliest clues came from binary star systems, where a visible star appeared to orbit an unseen companion. The motion of the visible star, combined with intense X-ray emissions, suggested that the companion was a black hole, quietly feeding on stellar material. These X-rays are produced in the accretion disk, where matter spirals inward, heating up to millions of degrees. Observatories like NASA's Chandra X-ray Observatory and ESA's XMM Newton have captured these emissions, allowing astronomers to identify and study black holes across the galaxy. The brightness, variability, and spectrum of the X-rays provide insights into the mass, spin, and feeding habits of the black hole. In recent years, a new window into black holes has opened: gravitational waves. These ripples in space-time, predicted by Einstein and first detected in 2015 by the LIGO Observatory, are produced when massive objects like black holes collide. The signal is faint, but unmistakable, a brief chirp that echoes across the cosmos. Each detection reveals the masses of emerging black holes, the energy released, and the nature of the final remnant. These observations have confirmed the existence of stellar mass black holes and provided clues about their population and distribution. Gravitational wave observatories, including LIGO in the United States, Virgo in Europe, and Kagra in Japan, continue to expand our understanding. They have detected dozens of black hole mergers, each one a cosmic event that occurred billions of years ago, now reaching us as a whisper in space-time. These detections have revealed black holes with unexpected masses, spins, and origins, challenging existing theories and opening new avenues of research. Another breakthrough came in 2019, when the Event Horizon Telescope, a global network of radio observatories, captured the first image of a black hole's shadow. The target was the supermassive black hole at the center of the galaxy M87, located 55 million light-years away. The image showed a glowing ring of light surrounding a dark center, the silhouette of the event horizon itself. This achievement confirmed predictions of general relativity and provided direct visual evidence of a black hole's existence. The Event Horizon Telescope has since turned its gaze to Sagittarius A, the supermassive black hole at the center of our own galaxy. In 2022, it released an image of this black hole, revealing a similar ring-like structure, though more challenging to observe due to its smaller size and dynamic environment. The image confirmed that the same physics applies across vastly different scales. Black holes, whether stellar or supermassive, follow the same rules, shaped by mass, spin, and gravity beyond imaging and gravitational waves. Black holes are studied through their influence on nearby stars and gas. In galactic centers, stars orbit at high speeds, suggesting the presence of a massive, invisible object. By mapping these orbits, astronomers can estimate the mass and location of the central black hole. This technique was used to confirm the existence of Sagittarius A, whose mass is about 4 million times that of the Sun. Black holes also influence the large-scale structure of the universe. Their jets and outflows can regulate star formation, heat intergalactic gas, and shape the evolution of galaxies. Observations of galaxy clusters, radio lobes, and X-ray cavities reveal the impact of black hole activity over millions of years. These effects are subtle but profound, guiding the growth and behavior of cosmic structures. Black holes may even influence our understanding of time itself. Near the event horizon, time slows dramatically due to gravitational time dilation. This effect, predicted by relativity and confirmed by observation, suggests that time is not absolute, but shaped by gravity. In extreme cases, time may nearly stop, offering insights into the nature of causality, entropy, and the arrow of time. Black holes, though deeply studied, remain among the most mysterious objects in the universe. At their core lies a paradox, one that challenges the very foundations of physics. According to general relativity, the singularity at the heart of a black hole is a point of infinite density, where space-time curves infinitely and the known laws of physics break down. But quantum mechanics, the theory that governs the behavior of particles at the smallest scales, does not allow for such infinities. Reconciling these two pillars of modern physics is one of the greatest challenges in science. One of the most intriguing ideas to emerge from this tension is Hawking radiation. In the 1970s, Stephen Hawking proposed that black holes are not entirely black. Due to quantum effects near the event horizon, pairs of virtual particles can form, one falling into the black hole, the other escaping into space. This process causes the black hole to lose mass over time, slowly evaporating until it disappears. Though Hawking radiation has not yet been observed directly, it offers a glimpse into the quantum nature of gravity and the fate of black holes. This leads to another profound question. What happens to the information that falls into a black hole? In quantum mechanics, information cannot be destroyed. Yet if a black hole evaporates completely, what becomes of the data encoded in the particles it consumed? This is known as the black hole information paradox, and it has sparked decades of debate among physicists. Some theories suggest that information is preserved in subtle correlations within Hawking radiation. Others propose that it is stored on the event horizon itself, encoded in a holographic form. The holographic principle, inspired by black hole physics, suggests that all the information contained within a volume of space can be represented on its boundary. This idea has profound implications, not just for black holes, but for the nature of the universe itself. It hints that reality may be fundamentally two-dimensional, with a third dimension emerging from encoded data on the cosmic surface. Another frontier in black hole research involves the possibility of wormholes, tunnels through space-time that connect distant regions of the universe. In theory, Certain solutions to Einstein's equations allow for such structures, and black holes may serve as gateways. However, traversable wormholes would require exotic matter with negative energy, something not yet observed. Still, the idea persists in science fiction and theoretical models, offering tantalizing visions of interstellar travel and cosmic shortcuts. Black holes also play a role in the search for a theory of quantum gravity, a unified framework that combines general relativity and quantum mechanics. String theory, loop quantum gravity, and other approaches attempt to describe the behavior of spacetime at the Planck scale, where quantum effects dominate. Black holes, with their extreme conditions, serve as natural laboratories for testing these ideas. They may hold the key to understanding the true nature of space, time, and reality itself in the coming decades. New observatories and missions will deepen our understanding. The James Webb Space Telescope, already peering into the early universe, may uncover clues about the formation of the first black holes. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers, revealing the dynamics of galactic cores. Ground-based telescopes will continue to refine our images of event horizons, capturing the dance of light and gravity with ever greater clarity. Artificial intelligence and machine learning are also transforming black hole research. By analyzing vast data sets from telescopes and simulations, algorithms can identify patterns, predict behaviors, and uncover hidden signals. These tools allow scientists to explore complex models, test hypotheses, and accelerate discovery. As technology advances, our ability to probe the darkness will grow, bringing light to the most shadowed corners of the cosmos. Black holes challenge our assumptions, stretch our theories, and invite us to question the limits of knowledge. They are cosmic riddles, wrapped in paradoxes, whispering secrets from the edge of understanding. They remind us that the universe is vast, mysterious, and filled with wonders yet to be discovered. And now, dear traveler, our journey comes to a gentle close. We have drifted through the birth of black hole theory, explored their physics, traced their growth, and uncovered the tools we use to observe them. We have peered into the future, where quantum mysteries and cosmic questions await. Through it all, black holes have remained silent companions, guiding us toward deeper truths. Thank you for joining me on this voyage through space and time. If you found peace in the stars tonight, consider subscribing, so we may continue exploring together. Rest well, and let your dreams carry you beyond the event horizon, into the heart of the cosmos, where mystery and wonder never end.